Hello students of statics, this is Dr. Dan Baker, and today we're going to talk about an introduction to moments. Now all of you should fundamentally know what a moment is, because a moment is the exact same thing that in physics you called torque. Now, I can't explain exactly why. Physics likes to call this rotational tendency of a force torque, and engineers like to call it a moment. But just know that wherever you see the word moment, it's exactly the same thing as torque. Okay, so once again, this is the rotational tendency of a force. So it is not a force itself. It turns out that moments slash torque and forces have different units. Okay, so as we look at a scalar equation for a moment, we can find that a moment, we tend to use the letter m. We always take a moment about a point, okay? So a moment will always have a subscript. And so this is going to be about point A. That's going to equal some force times d perpendicular, okay? And so this d perpendicular is defined as a perpendicular line a perpendicular distance from the point of interest. So we're talking about point A to the line of action of the force. Let's abbreviate line of action LOA, line of action of the force. So if you're able to find a perpendicular distance, this is a very simple computation. Now the only additional thing that comes into this relationship is that the sine comes from the right-hand rule. So to show you an interactive of what this looked like, let's go ahead and look at this interactive. So we have this interactive is we have a wrench. And we have essentially this wrench is centered here around point A. We have a force applied to this wrench. In this case, we're pulling on this wrench toward us. And what we see is that provides a moment from the right-hand rule, which is positive. Fundamentally, if we pull in this direction, we would expect that bolt or that nut, whatever this wrench is attached to rotate in that same direction as the moment. Now, something that happens here as we move this force line of action, right? Remember the force line of action comes through the force vector, is that notice if we pull on the end of the wrench, kind of lengthwise, our moment completely goes away. If we push on this wrench in this direction right here, we'd actually end up with a moment in the opposite direction. This would be negative from the right-hand rule. And so we have this relationship between this force and this position vector going between the wrench over to point A. So to show that a little bit more explicitly, let's take a look at this interactive. It has a little bit more going on. We show the line of action of that force. We show here D perpendicular. Okay, so here's D perpendicular, always going to stay perpendicular to that, that force vector. And so in this view, we can see that if we cross this D perpendicular into the force vector, right, sliding your fingers along D perpendicular, curling them into the red force vector, your thumb should go down into the screen and you should end up with a negative moment. If we flip around our force vector, pulling on that wrench, this would classically be what's called left lefty-loosey, right? We want to loosen up this nut as opposed to righty-tighty going the other direction. And we notice that we take this D perpendicular, cross it into our force vector, and we end up with a positive moment from the right-hand rule. Now, something you've probably seen lurking in here is this second position vector r. And it turns out that we don't always have to find the D perpendicular. You can also find any vector which connects our point of interest with the line of action of this force. And so technically we could be pointing right here at the end of the handle. We also could have drawn an R that went up here on the line of action. Any of those R's, just like this D perpendicular is a special case of R, would give us the exact same moment around point A. So coming back over to our notes, we could write that the vector equation for a moment is that the moment around point A as a vector is equal to R cross F. And again, just to put this in words, we could say that this R is defined as any vector from the point of interest Now we talk about this point of interest. This is the point we're taking the moment around, right? It's this point right here. So from that point of interest to the line of action of the force. Now practically, there's usually not that many R vectors to pick from, right? We're going to have a certain kind of geometry specified in a problem, and we're going to use that geometry to basically solve what's going on. So that's the general equations for a moment. So if we combine these general equations with our knowledge of cross products, it turns out that there are fundamentally 4 different ways to solve a cross product. So on this page, we're going to talk about these 4 different ways, and we're also going to talk about in which of them do you have to do essentially do a manual right-hand rule, and which of them are going to be kind of built-in right-hand rule. And we'll also talk about the preferred methods for 2-dimensional vectors versus 3-dimensional vectors. Okay, so as we go down through this list, we show that the first technique is a vector determinant. So with a vector determinant, it turns out that our right-hand rule is built in. So you don't have to do any manual right-hand rules with a vector determinant. Now, if you don't know how to take a vector determinant, take a look at the previous video on vector cross products, and you can see how those are computed. The second way that we could compute an R cross F moment is coming back to our definition of a moment. And the definition is M is equal the length of R, right? The magnitude of R times the magnitude of F times the sine of the angle between those times this unit vector u hat, right? Remembering that u hat is perpendicular to both R and F with its sign coming from the right-hand rule. Finding the direction of u hat on a 3-dimensional problem is really hard. But on a 2-dimensional problem, it can be quite easy. Every single u hat in a 2D problem is going to be either in the k hat coming out of the page or in the negative k hat going into the page. So while using the right-hand rule for this equation is a manual process, it is easy in 2D, but hard in 3D. Okay, so I wouldn't use this equation ever in 3D, and I would honestly rarely use it in 2D, and we'll talk about that as we move forward. So a third option, so we'll pick up on the ones that we've already discussed, and that would be to find our moment. Now, all of these moments will be vectors. And I'm just going to put a general point here, point O, being the point of interest. And so a moment about O equal to a magnitude of F, a distance d perpendicular, and then if I multiply this times the same unit vector u hat, I can turn that scalar moment into a vector moment. And once again, this is going to be requiring a manual right-hand rule because you need to determine the sign on that u hat. And once again, u hat in 3 dimensions is really hard to find. In 2 dimensions is not too hard, right? Because it's going to either be positive or negative in or out of the board. And so then the last way to look at these moments is what's called the principle of moments. And the idea behind the principle of moments is we want to find the perpendicular pairs of the components. Okay, so we want the perpendicular component pairs. Because we know that all the parallel pairs, all of, say, if I write out my determinant here, Rx let me use a determinant to write out these different components, I hat, j hat, and k hat, Rx, Ry, Rz, Fx, Fy, Fz. So we know that if I cross any of my x component terms, if I crossed my Rx into Fx, I get a 0. Ry into Fy, I get a 0. Rz into Fz, I get a 0. So on a 2-dimensional problem, we know that there are no z components. Okay, so Rz and Fz would go to 0. So all we're left are the pairs of Rx, Ry, Fx, Fy, the perpendicular pairs. And so the only components that are left out of this 2-dimensional determinant, and you've probably seen this equation before, they're both going to be k-hat components. We have an Rx times Fy, and then subtract from that our Ry times Fx. I'll put this in parentheses because this entire thing is times k-hat. Now, if you like using this version of the equation, it's not a wrong thing to do, but you need to realize exactly what's happening. You need to bring in any of the negative components into this equation, because fundamentally in this equation, you've already done the cross product. Okay, you've already basically done the I hat crossed into j hat is positive k hat, and then the j hat crossed into I hat is a negative k hat. That's where you get this negative sign here in the middle of the equation. And so like I said, you have to bring in these terms. But what we've recognized in this equation is that these are our perpendicular pairs. So whether you think about them kind of in total like this, or if you think about them, and this is the way I typically think about them more, is that I have an Rx, which is a component vector, and I'm going to cross that into Fy, which is a component vector, and then I'm going to add that to my Ry crossed into Fx. So I'm going to cross each one of those component vectors, then add together the answers, and I'll still end up with a k-hat value exactly equal to the one above. And so in the principle of moments, it is a manual computation of the right-hand rule. But the nice thing about it is it basically ignores all the other components that you don't need to worry about and only focuses on those that are perpendicular. So in my opinion, I think that this principle of moments is the best choice for 2D. And if I'm doing a 3-dimensional moment, I tend to choose a vector determinant. So this would be best for 3D. While the other techniques, number 2 and number 3, work, quite honestly, the geometry in finding this D perpendicular is non-trivial. It can take a fair bit of effort. And then, as I mentioned, finding the direction of U hat on a 2-dimensional problem is pretty easy in or out of the board. And certainly if you already have this sign of angles in between them, you could jump right into that technique versus the principle of moments. But often vectors are expressed more in components. And so if you have the components, you're best to go into principal moments as opposed to needing to solve for that angle between those vectors in technique number 2. So hopefully this helps you kind of think about 4 different ways to solve R cross F moments. None of them are wrong. They just have different advantages and disadvantages. And in the upcoming example, I'll show you how to compute a 2-dimensional moment using these different techniques. Hope you're having a great day.